Okay, so in this video we're going to talk about the chain rule. And the chain rule is used whenever we have composite functions, so like f of g of x. So we'll use a capital F to notate the composite function, and then we'll use lowercase, kind of like we normally do. So we're going to have a function inside another function, so f of g of x. So if this is our original function, then the way we're going to find the derivative using the chain rule is to find the derivative of that outside function, and the inside will not change for that step, times the derivative of the inside function. So really the most that you have to do for these problems is identify what the inside and outside functions are. Okay, so maybe label those just for your definition so that in a second when we kind of break it apart that way it'll make more sense. Although let's be more specific. We'll say outside derivative, then the inside, and then this is technically the inside derivative. There, that makes a little more sense. Oh, when I abbreviate I don't want to put the E there. Okay. So for each of our examples we're simply going to differentiate. Okay, so our first example is going to be whenever y equals x squared plus 1 raised to the 100th power. Okay, so first let's go through this process of identifying the inside and the outside function. Okay, so the inside function is easier for me to find first because it's whatever I would plug something into if I were evaluating the function. So for this one, I can see that the inside is going to be x squared plus 1. Okay. And I'm going to kind of write it down below. That'll make sense in a minute. So inside is going to be our g of x function, if it's f of g of x, and that's going to be x squared plus 1. Now what I'm plugging it into is the outside function, which is this part outside of the parentheses, which is raising the function to a power of 100. Okay, so our outside function is going to be x to the 100th power. Okay, so if it's f of g of x, then we're basically taking x squared plus 1 and substituting it into x to the 100th power. Alright, so let's actually try to work through this. So I'm going to rewrite the problem in color. You do not have to do that, obviously. I'm just trying to make it a little bit easier to follow. So our outside function is something raised to the 100th power. Our inside function is x squared plus 1. And now we're going to find the derivative. So dy over dx will equal f prime of x, or the derivative of the outside, which means using the power rule, taking 100, bringing it down front. So 100 times whatever that is, and then it goes down a degree. The inside does not change. Then I'm going to multiply by the derivative of the inside function, which again I just use the power rule for, and that becomes 2x to the first, and then plus 0, which I'm just going to leave off. Okay, and now we can just clean it up from here. So that means that dy dx, I can multiply the 2x and the 100 and simply get 200x times x squared plus 1 to the 99th power. And we love the chain rule because otherwise, if you saw a problem like this, you would be doing the power rule, but man, that would be a lot of multiplying. So we're very grateful that we have the chain rule to begin with. Alright, so for the second example, we're working with the function y equals the square root of 3x squared plus 5x minus 2. Okay, so here we have The outside function and the inside function looks like it's just going to be what's underneath the radical. The outside function will just be the radical itself. So let me make sure I use the same colors. So I use blue for inside. So that's going to be the 3x squared plus 5x minus 2. And that's going into the outside function, which is just square root x, right? So we're doing f of g of x, which means that's what's getting plugged in. However, whenever we have radicals in the past, we always want to rewrite these as powers, which are just rational exponents. So I'm going to take a second and rewrite this with a 1/2 exponent, which means I'm also going to rewrite this guy over here as x to the 1/2 being our outside function. Alright, so again, I'm going to rewrite it in color. You do not have to do that. So our outside function is the square root. The inside is the 3x squared plus 5x minus 2. So for dy over dx, we're going to take the 1/2, bringing it down front. Leave everything inside the same, take away a power of 1, and then take the derivative of what's inside, the 3x squared plus 5x minus 2 will become 6x plus 5. Okay, again, not a lot to clean up here, but I do want to go ahead and rewrite it as a fraction, just for good practice. So we can see we have the fraction 1 over 2, so I'll just start with that. The 1 on top, the 2 on the bottom. Since this whole parentheses has a negative exponent, it also will go to the bottom. Oh, and you know what? I'm going to go ahead and rewrite it as a square root too. So 3x, sorry, I'm running out of space. 3x squared plus 5x minus 2. It's going on the bottom, and then the 6x plus 5 is still on top. You can put it like this, but, whoa, except with a 5. But what I'm about to do in a second is just multiply a 1. So I don't really need the 1 or the parentheses there, so I'm just going to get rid of that. And I'm just going to leave the numerator as 6x plus 5. And that would be the way you would see it on a multiple choice answer. Obviously, if you're just doing work for me or on an open-ended question, you can leave it in that other form. Alright, for our last example, we're going to work with y equals 1 over x squared plus x to the 4th. Now, obviously, for this problem, you could just do the quotient rule, like you don't have to do the chain rule. And that's the thing with derivatives, there's a lot of times more than one way to do a problem. But we're going to try it with the chain rule just to see how it works. Alright, so the inside function, or where I would start to plug something in, would be right here in the denominator. And it's the, let's see, x squared, he's always g of x, the inside. That'll be x squared plus x to the 4th. What I'm plugging it into is that denominator, which means that 1 to the x would be our outside function. Okay, so I'm going to rewrite it using these colors just to help me. You do not have to, but basically, before I do that, let's go ahead and rewrite this, because I don't normally leave it as a fraction when I'm breaking it into 1 over x or 1 over anything. We can just write that thing with a power that's negative instead, so that would help me out a lot here. So then that means that this outside function is really something raised to the negative 1, which is important. Okay, so that's my outside function. The inside part is the x squared plus x to the 4. Now let's do the chain rule. Okay, so dy dx, that negative 1 is going to come down front, multiply whatever's there, and then the power drops down to negative 2. That inside function is x squared plus x to the 4th. Then I'm going to multiply by that derivative, which would become 2x plus 4x cubed. Alright, again, the cleaning up will just be writing stuff as a fraction to get rid of this negative denominator. So I have a negative 1 on top, I have this x squared plus x to the 4 on the bottom, so that becomes a positive 2, and then I have that 2x plus 4x cubed on the numerator, or in the numerator. So then all I have left to do here is just distribute the negative 1, and we'll be done. So our final answer will be negative 2x minus 4x cubed over x squared plus x to the 4 all squared. And this should make us feel good, right? Like if we had done this original problem using the quotient rule, low d high minus high d low over low low, low low, denominator squared. And as you can see, when we simplify it, that's what we end up with here. So you could do it either way. Obviously these can get a little bit more difficult. We can involve trig. We could have more than just two functions. And so we will work on these harder problems, but this concludes our introduction lesson to the chain rule.